Welcome back for another deep dive. Today we're going inside our devices to look at computer hardware and how it talks to the software we use every day. Have you ever wondered how your computer understands what you want it to do?
Right.
We're going to find out.
Yeah.
Our source material, a really cool excerpt on the hardware-software interface.
Like a secret language that makes our digital lives possible.
Okay, let's unpack this whole hardware-software tango. Instead of diving straight into the technical jargon,
Right.
picture this. Your computer is like a grand orchestra.
I like where this is going.
You got your strings, your brass, your percussion, right? All these different instruments working together to create something amazing. And in a computer, these instruments are your hardware components. The hard drive, the graphics card, the network adapter, each with a specific job to do.
And just like an orchestra needs sheet music, so everyone is playing the same tune, our hardware needs instructions, and that's where device drivers come in. They're like the musical scores, right? Translating the operating system's commands into something each hardware component can understand.
So device drivers are like the multilingual crew backstage, making sure everybody's speaking the same language.
Exactly. Each device has its own, unique driver, a specialized translator for that particular piece of hardware. Now, imagine a conductor, right? Organizing all these instruments into sections. The strings, the brass, the woodwinds, that's kind of like the I/O hierarchy in a computer. It groups different devices by their function. You've got block devices for storage, character devices for input and output, and network devices for, networking.
Wow, that's some serious organization. But why go to all this trouble? Why is standardization so important?
Because it allows for flexibility and innovation. Without it, adding a new device would be like inventing a whole new instrument and teaching the entire orchestra how to play it. Right. Instead, standardized instructions act as a universal language, allowing new devices to join the symphony seamlessly. Think about it. You can plug in a new printer or camera, and your computer just knows what to do. That's the beauty of standardization.
That makes so much sense. Every time I connect a new gadget, I'm basically expanding my computer's orchestra with a brand new instrument ready to play. But how do those instructions actually get to the hardware? What's that communication process like?
That's where things get even more interesting. One method is called programmed I/O with polling.
Lead me down the technical rabbit hole. What is polling exactly? So programmed I/O with polling. It sounds very official. Break it down for me.
Okay, so imagine you're sending a text message.
Okay.
And you're really impatient to get a response. So you just keep checking your phone every few seconds, right? That's essentially what polling is. The CPU constantly checks in with the device to see if it's ready.
Okay, so the CPU is like that friend who's just texting you there every 5 seconds.
Exactly.
Got it. But how does the CPU actually send instructions to, say, the hard drive? What are those instructions like?
So think of it like this. The CPU has this little notepad.
Okay.
And it writes down very specific commands for the hard drive, like read data from sector X. These commands are stored in special mailboxes called registers.
Okay.
So there's a register for the command itself, like read or write, and there are other registers for specific details, like what data to read or where to write it.
So it's like a whole mini postal service inside the computer.
Yeah.
The CPU drops a detailed instruction note into the hard drive's mailbox. What happens next? Does the CPU just wait around for the hard drive to finish?
Not exactly. So the hard drive has its own set of mailboxes or registers. One important one is the busy flag.
Okay.
It's like a little sign that says busy or available.
Right.
The CPU keeps checking this flag, and when it sees available, it knows the hard drive has finished the task, and then it's ready for the next instruction.
Okay, so that's the polling part.
Yes.
It's constantly peeking at that little busy sign to see when the hard drive is free.
Precisely. And once the task is complete, the hard drive drops the results into another mailbox, which is called the data buffer.
Okay.
It's like the hard drive's outbox.
Right.
The CPU can then pick up the results from the buffer.
This system seems pretty straightforward. But something tells me there might be a downside. Can't be that easy, right?
You're right, there's a trade-off. While simple, polling can be inefficient, especially with large data transfers or super fast devices. So imagine you're downloading a huge file.
Right.
And the CPU is stuck constantly checking if each tiny bit of data has arrived.
Yeah.
That would be a huge waste of time.
It'd be like watching the progress bar move at a snail's pace.
Exactly. In those situations, interrupting the CPU's other tasks to constantly check on the device slows everything down. That's why polling is generally used for quick exchanges, or in systems where the CPU isn't juggling tons of tasks.
So polling works well for like the small jobs. But what about when we're talking about massive downloads, streaming movies, or just having a million tabs open? Is there a more efficient way to handle those situations? So if polling isn't always ideal for a busy computer, what's the alternative? How can we make this communication more efficient?
Well, imagine instead of constantly checking your phone for a message, you simply receive a notification when one arrives. That's the basic idea behind programmed I/O with interrupts. It's like saying, just let me know when you're done.
Okay, so instead of the CPU acting like that impatient friend who keeps texting, the device sends a signal when it's finished with its task.
Precisely. The device can send an interrupt signal to the CPU. This signal is like a virtual tap on the shoulder saying, hey, I finished that file transfer. The CPU can then handle the data without needing to constantly check in.
That sounds much more efficient. It's like the difference between constantly refreshing your inbox and just waiting for that notification ding. So instead of babysitting the hard drive, the CPU can focus on other tasks until it receives that interrupt signal.
Exactly. It's all about making the best use of the CPU's time. Think about it. If your computer had to constantly poll every single device connected to it, your keyboard, your mouse, your internet connection, everything would slow to a crawl.
That makes total sense. Interrupts let the CPU multitask like a pro. But are there any downsides to this approach?
Well, there's always a trade-off, isn't there? While generally preferred in a busy system, interrupts do add a tiny bit of overhead. Processing the interrupt signals and switching between tasks requires a bit of CPU effort.
So it's like the CPU is willing to be interrupted, but it still needs a moment to like switch gears and address the new task?
Precisely. But compared to the constant back and forth of polling interrupts are still far more efficient for most modern computing needs. They're the reason why your computer can handle playing music, browsing the web, and editing documents all at the same time.
That's amazing. Now, we've talked about polling, we've talked about interrupts, but I've heard rumors of an even more advanced technique for data transfer, something called DMA. What can you tell me about this mysterious DMA?
Direct memory access, or DMA. This is where things get truly impressive. Imagine you have a massive delivery of boxes arriving at your house. Instead of you carrying each box one by one, you have a dedicated moving crew that brings everything in and puts it directly where it needs to go. That's DMA in action.
So the CPU is basically saying, here's the data, here's where it goes, and then the DMA controller takes over like an efficient moving crew, freeing up the CPU to like relax, put its feet up.
Exactly. With DMA, the CPU delegates the data transfer task, specifying what needs to go where. Then the DMA controller takes over moving data directly between the device and main memory without bothering the CPU. This is especially crucial for those data-heavy tasks like downloading huge files or streaming high-definition videos.
That's incredible. It's like having a whole separate engine dedicated to handling these large data transfers, leaving the CPU free to do other things. No wonder my computer doesn't turn into a molten mess when I'm downloading gigabytes of data.
It's quite a marvel of engineering, isn't it? And as our need for speed and efficiency grows, DMA technology is constantly evolving and improving. Just think, without DMA, we'd be stuck waiting ages for even the simplest tasks to complete.
This whole deep dive has been a real eye-opener. From device drivers acting as translators between hardware and software, to the cleverness of interrupts, all the way to DMA controllers orchestrating massive data transfers, it's like peeking behind the curtain of our digital world.
It's a hidden symphony of coordination happening every time you click type or stream. And the amazing thing is most people never even realize it's happening.
I have to say, I have a newfound appreciation for all the intricate communication happening inside my devices. And for our listeners, next time you hit download or watch a video or just marvel at how fast your computer is, remember the magic of hardware and software working in perfect harmony.
And who knows what the future holds? As technology continues to advance, who can say how this intricate dance between hardware and software will evolve? It's a truly exciting time to be a tech enthusiast.
Absolutely. Well, that's all the time we have for today's deep dive. A huge thank you to our expert for joining us on this fascinating journey into the heart of computer hardware. Until next time, keep exploring, keep questioning, and we'll see you on our next deep dive.
Ever find yourself streaming music while simultaneously emailing, and somehow your computer just handles it? It's kind of wild when you really think about all that data flying around, right?
Yeah.
Well, a lot of that magic, a lot of that seamless multitasking you're enjoying, you can thank data buffering for that. And that, my friend, is exactly what we're diving deep into today.
Absolutely, though I promise it's way more interesting than it maybe sounds.
Right. buffering, not exactly the most thrilling word in the English language.
Yeah.
But trust me, it's one of those things that once you understand it, you start seeing it everywhere. Kind of like, I don't know, learning a new word and then suddenly it's like every other sentence on the radio. So are you ready to unlock the secrets behind lightning-fast apps and seamless multitasking? Let's dive in. Now, picture this. A world without buffers. It'd be like, I don't know, trying to have a conversation where everyone's talking at the exact same time, utter chaos. And honestly, that's kind of the problem buffering solves, isn't it?
Yeah, it's like, imagine you've got a messenger, right? They're delivering a package, but instead of a person, it's your computer sending data.
Okay, I'm with you.
Without a buffer, that sender and the recipient, they got to be totally in sync. Like, one ready to send, the other ready to receive at that exact nanosecond.
Which, in the digital world, is basically impossible. Everything's moving way too fast.
Precisely. But that's where our hero, the buffer, swoops in. It's like having, say, a mailbox.
Ooh, okay, I like this analogy.
So the sender, let's say your keyboard can drop data into that buffer anytime it wants. Then the recipient, your computer's processor, can swing by, pick it up, process it at its own pace.
So essentially, this buffer acts as a temporary holding space, making sure nothing gets lost in translation.
You got it. And this is happening constantly, even with the simplest stuff. Like when you're typing on your keyboard, ever notice how if you're really on a roll, the letters might lag a bit on the screen?
Oh yeah, actually, now that you mention it.
That, my friend, is your keyboard buffer doing its thing, holding those keystrokes hostage. I mean, politely queuing them up until the computer can catch its breath.
A little digital cue to keep those data packets flowing. I love it.
Exactly. And it gets even cooler. This buffer, it's not just passively holding stuff. It can actually transform the data, too.
Oh, really? Like how?
Think about when you type those special characters. In the symbol, the hashtag.
Right.
Those often need a combo of keys. And the buffer, it steps in to translate that keystrip combo into the right symbol before it even gets to your document.
So it's like going from raw ingredients to a delicious cooked meal.
Yeah.
The buffer does all the behind-the-scenes prep.
Nailed it. And that whole data transformation thing, crucial for stuff like encoding videos, decoding music files, all that good stuff that keeps your entertainment running smoothly.
Okay, so we've got our single buffer, working hard, holding onto that data, keeping everything running nice and smooth, host speaker. But what happens when things, escalate?
Right.
Like when you're trying to stream the latest blockbuster 4K resolution, all the bells and whistles, or maybe downloading like a massive file, host speaker, and the data's just coming in, I don't know, faster than like a pack of Cheetos on roller skates, something ridiculous.
There you go. That's when we got to upgrade from single buffering to something a little more heavy duty.
Ooh, okay, do tell.
Buffer swapping.
Buffer swapping. I like the sound of that already.
So picture this.
Yeah.
You've got not one, but two buffers.
Okay. Two is always better than one, right?
Exactly. So while one buffer is busy catching all that incoming data, the other one's already prepped and ready to take over the second that first one gets full. It's like a relay race. You got your runners seamlessly passing that baton to keep the momentum going.
So it's all about that constant flow, never letting things get backed up, even with those massive amounts of data.
You got it.
Okay, I think I'm getting this, but let me play devil's advocate for a second.
Hit me with your best shot.
What if even two buffers just aren't enough?
Okay, I see where you're going with this.
What if we're talking about a data deluge of like epic biblical proportions, a tsunami of information?
You're thinking big picture, which I love. For those truly extreme cases, when even buffer swapping just won't cut it, we bring in the big guns.
And the big guns are?
A circular buffer.
Circular buffer? Okay, I'm not gonna lie, that sounds a little intimidating.
It's actually pretty elegant when you break it down. So imagine a circular track. Like those old school car racing games, where you just go round and round.
Yeah, I can picture that.
So circular buffer, it works kind of like that. It's still a fixed size, but instead of having a start and a finish, it just continuously overwrites the oldest data with the newest as it goes around.
So it's like a digital merry-go-round, constantly loading and unloading without ever actually stopping?
You're getting it. And the beauty of this whole thing, it handles those unpredictable data bursts like a champ. Even if there's this sudden surge, that circular buffer, it just keeps on chugging along, smooth and steady.
Man, it's incredible how much thought goes into these things that most of us never even realize are happening.
Right. But that's what makes this stuff so cool.
So from single buffers to these tag teaming duos and now these endlessly looping circular buffers, it's like...
It's a whole world of data management.
Exactly. It's a whole world most people don't even know exists, and yet it's the backbone of how we experience everything digital.
Wow, we've covered some serious ground today, haven't we?
We really have, from those single buffers to the whole swapping thing.
Right, and those circular buffers. Mind-blowing.
It's like a whole hidden world keeping our digital lives ticking.
Totally. But before we wrap up, there's one more term we got to talk about. One more player in this whole buffering game.
Oh, you mean caching?
Caching, exactly. And I know sometimes it feels like buffering and caching are just used interchangeably. And you know what? They often are. But there's a reason for that. Because at their core, they're both about that same basic idea.
Which is?
Storing stuff temporarily to make things, faster, more efficient.
Okay, so like a family reunion, but for data optimization techniques.
Exactly. But caching, it's got its own little flair. So think about it this way. Imagine having to search your entire house for a specific book every time you needed it.
Ugh, my nightmare. I'm already stressed just thinking about it.
Right. Well, accessing data from your hard drive, it can be kind of like that. A lot of searching, a lot of waiting.
Okay, I'm seeing where you're going with this. So caching is like...
Caching is like having that bedside table, right?
Yeah.
Where you keep your absolute favorite books, the ones you're always coming back to, right there within arm's reach.
Gotcha. So it's all about predicting what you'll need and having it prepped, ready to go in a flash.
Nail it. And you know what's really cool? Your operating system, it's actually crazy good at managing this whole caching process.
Really? So it's like the OS has a sixth sense for what I'm going to do next.
Pretty much.
Yeah.
It uses these different lists to organize all that cached data. Like, imagine a super organized library, but for data.
Okay, I can dig it. So different lists for different types of data. Makes sense.
Right. So there's these locked lists, right? That's for essential stuff, stuff the system needs constantly.
Important documents, top secret files, that kind of thing.
Exactly. Then you've got your LRU lists, stands for least recently used.
LRU. Okay, so it's like a priority ranking system.
You got it. Prioritizes the data you've used recently, figuring you're more likely to need it again soon. And of course, you're going to have some free space in the cache too, just in case.
Makes sense. Got to be ready for those unexpected data deliveries.
Always got to be prepared.
So as we wrap up our deep dive today, it's kind of amazing, isn't it? This whole hidden network of like temporary storage solutions all working together to make our digital lives bearable.
It really is.
From those elegant single buffers to the tag team duo of buffer swapping to those endlessly looping circular buffers, it's like a symphony of data management happening right under our fingertips.
A symphony that most people never even hear.
Exactly, but that's kind of the beauty of it, right? It just works seamlessly. So next time you're streaming a movie or typing an email or just browsing the web, maybe take a second to appreciate those invisible heroes, the buffers and caches, working tirelessly behind the scenes. Thanks for joining us for this deep dive. We'll catch you next time for another adventure into the fascinating world of tech. Ever get frustrated by that spinning wheel of doom, waiting for your computer to catch up?
Yeah.
We've all been there. You click a file and crickets.
Exactly.
But what you might not realize is there's this like hidden world inside your hard drive where this constant battle for speed is being waged.
Yeah.
And the secret weapon in this battle, disk scheduling algorithms. You sent us some fascinating articles on this, so buckle up, we're diving deep.
Yeah, I'm excited.
Now, I know disk scheduling might sound about as exciting as like watching paint dry, but trust me on this one. Okay. It's surprisingly fascinating, and more importantly, it directly affects how fast your computer runs.
It really does. It's true. We often take for granted how quickly we can access files on our computers. Yeah. But behind the scenes, there's a sophisticated dance happening to make that possible.
Okay, let's unpack this dance, shall we?
Yeah, let's do it.
Imagine this. Your hard drive is like a vinyl record, right?
Okay.
But instead of music, it's holding all your digital life photos, documents, the embarrassing video from your friend's birthday party.
Yep, it's all there.
It's all there.
Uh-huh.
And just like A record player has a needle that reads the grooves.
Hmm.
Your hard drive has something called a read-write head.
Right.
This little arm has to physically move across the spinning disk to find the exact data you're looking for.
It does.
Now, those grooves on our imaginary record.
Okay.
On a hard drive, we call those tracks.
Mm-hmm.
And each track is split into smaller segments called sectors.
Right.
So when you click on a file, the read-write head needs to first locate the correct track. That's called seek time.
Right.
And then it has to wait for the right sector to spin underneath it.
Yep.
That's rotational delay.
Uh-huh.
All of this takes time, even if it's just milliseconds.
It does. And those milliseconds really add up.
Oh, yeah.
Especially when your computer's juggling multiple requests at once.
Oh, absolutely.
Think about opening a large application while also streaming music and browsing the web.
Oh, man.
Your hard drive is handling a symphony of requests, all vying for its attention.
Oh, it's a symphony of chaos.
It is. It really is.
So it's like a rush hour traffic jam inside our hard drives.
Yeah, exactly.
Except with ones and zeros instead of cars.
With data.
Yeah. And just like we have traffic lights and rules of the road to manage traffic flow, computers rely on disk scheduling algorithms to, like, direct this constant flow of data requests.
Exactly.
Okay, so how do these algorithms actually work?
Yeah, how do they work?
Give us the inside scoop.
Well, the simplest one is called FIFO.
FIFO.
For in, first, out.
Okay, got it.
Imagine a line of people waiting for their morning coffee.
Okay.
FIFO is like a barista who serves each person in the order they arrived,
Okay.
no matter what they ordered.
Right.
Right.
Sounds fair, but maybe not the most efficient.
You got it.
Yeah.
Let's say the first person in line wants like a complicated latte,
Okay.
and the next person just needs a black coffee that's already brewed.
Mm-hmm.
With FIFO, the barista would spend all their time on the latte
Right.
while the second person waits, even though their order would take a second to prepare.
Oh, I see the problem.
You see it.
So in hard drive terms,
Yeah.
that means the read-write head could be bouncing all over the disk,
Exactly.
chasing after requests in the order they came in,
Yes.
even if there's a quicker option nearby.
Exactly. That's where a slightly more clever algorithm comes
Yeah,
in.
okay.
SSTF, or shortest seek time first.
SSTF.
This one's all about efficiency.
Okay, so how does SSTF help our poor, overworked read-write head?
Think of SSTF as a highly organized barista
Okay.
who can see all the orders lined up.
Okay.
Instead of going down the line in order,
Yeah.
they prioritize the quickest requests first.
I like this at barista.
So they'd serve that black coffee while the latte is steaming.
Okay.
They'd move on to the next fastest order, minimizing the amount of time spent running around.
So it's like optimizing the route of the read-write head.
Exactly. With SSTF, the read-write head prioritizes requests that are closest to its current position,
Okay.
minimizing those back and forth movements across the disk.
So less seek time
Less seek time,
and faster access to your files.
which means faster access to your files. You got it.
So that's why my apps sometimes open faster.
It could be.
It's all thanks to SSTF playing traffic cop inside my computer.
Yeah, it's possible.
Yeah.
But just like any traffic system, SSTF has its drawbacks.
Oh, no.
Remember how we talked about fairness with the FIFO approach?
Right. Everyone gets their coffee in the order they came in, even if it takes a bit longer.
Well, SSTF sometimes struggles with that concept.
Oh, really?
It's so focused on efficiency that requests for data on the outer edges of the disk might get stuck waiting longer if closer requests keep popping up.
Oh.
It's like our barista constantly getting distracted by new customers ordering simple drinks, while that one person waiting for a double-shot extra foam cappuccino is stuck waiting forever.
So SSTF is like this speed demon?
Yeah.
But it might leave some requests like feeling a bit neglected in the pursuit of efficiency.
It's a classic trade-off.
Yeah.
And it highlights a crucial point. There's no one-size-fits-all solution when it comes to disk scheduling.
So it's more complicated than just finding the fastest algorithm then.
Absolutely. In reality, operating systems often use a combination of algorithms and techniques,
Oh, wow.
constantly adapting to the types of requests coming in.
Oh, interesting.
If you're doing a lot of small random tasks like browsing the web,
Ah.
one approach might be better. But for something like video editing, where you're accessing large files
Right.
sequentially, a different strategy might be more efficient.
So it's a bit like those self-driving cars we're always hearing about,
Yeah.
constantly making decisions based on real-time data and trying to optimize for the best outcome.
A great analogy.
Yeah.
And just like with self-driving cars, there's a lot of ongoing research in the world of disk scheduling,
Really?
always searching for more intelligent and adaptive algorithms.
That's so cool. You know, diving into this really makes you appreciate all the hidden complexity
It does.
that goes into making our computers run smoothly.
It really does.
Yeah.
And it highlights the power of thinking critically about even the most mundane seeming aspects of technology.
Yeah.
We often take for granted how seamlessly things work.
Yeah.
But there are brilliant minds behind the scenes, constantly tinkering and optimizing to improve our digital lives.
To our listeners, the next time you open a file or launch an application,
Yes.
take a moment to think about the incredible dance of data happening beneath the surface.
Yeah,
It might just change the way you interact with your devices.
it might.
This deep dive has certainly given me a newfound appreciation for the unsung heroes of computing,
Uh-huh.
disk scheduling algorithms.
Yeah.
Until next time, keep exploring, keep learning.
Keep learning.
And thanks for joining us on The Deep Dive.
Have a scroll through your phone like frantically searching for a photo, and it's just gone. Yeah. That sinking feeling of potential data loss. That's what we're tackling today. We're going deep into the systems that keep our digital lives from vanishing into thin air. Now, our source material is a bit technical. Think excerpts from an operating systems textbook. But stick with us, we're going to make it clear. And dare I say, fascinating. Think of your data like ingredients perfectly organized in containers on your kitchen shelves. Those containers, those are your disk blocks or sectors, the basic storage units on a hard drive. So what happens when those digital containers fail? What causes our data to go bad in the first place? I've got our expert here to break it down for us.
Well, our source points to two main culprits. The first is a system crash that occurs right in the middle of a write operation. Imagine you're baking a cake. Everything's going perfectly, and suddenly, power outage. The oven shuts off before the cake is fully baked. That's essentially what a system crash does to your data mid-write. It leaves it in a partially updated, completely unusable state. Not very appetizing, is it?
Definitely not ideal, especially if it's, say, an important document instead of a cake.
Exactly. And the second culprit is a bit more insidious because it happens gradually. The physical degradation of your storage media. Over time, those containers holding your data, the disk blocks, can deteriorate.
Yeah.
Just like anything else in the physical world, they can become damaged, making it impossible for your computer to reliably read or write data.
So it's like finding a cracked container of flour in the back of the pantry. Not ideal, but also kind of to be expected after a while.
Precisely. It highlights the importance of things like backups and caress, as we'll discuss. The clever systems designed to catch these errors before they become major problems.
Okay, so we've got these potential data disasters waiting to happen. What's stopping our digital lives from descending into chaos?
That's where some really elegant error handling techniques come into play. And the beauty is, they're often based on incredibly simple concepts. Let's start with parity bits.
Parity bits. Okay, that throws back to some tech class I probably should have paid more attention in. Can you break that down for me? And for everyone else who might be drawing a blank on parity bits.
Absolutely. Think of it like this. You know how you always make sure you got both socks after doing laundry, right?
Who doesn't? Mismatched socks are the worst.
Exactly. Parity bits are kind of like that. But for your data, they're a system for detecting errors. And it all comes down to a simple even or odd check. Every time your computer stores a chunk of data, remember those containers we talked about? It adds one extra bit, the parity bit.
Just one little bit. That seems surprisingly straightforward for something so important.
Don't let the simplicity fool you. It's incredibly effective. This parity bit acts as a check to make sure the data hasn't been corrupted. Let's say we're using an even parity system. The system will ensure that the total number of 1 bits in the data, including that little parity bit, adds up to an even number. If something changes in the data, like one of those 1 bits accidentally flips to a 0, the parity check will fail, and the system immediately knows something is wrong.
So it's like a tiny alarm bell going off saying, hey, something's not quite right here.
You got it. It's a simple but powerful way to detect errors.
That's really clever. But it also makes me wonder, what if more than one thing goes wrong? Can parity bits handle that? That's really clever. But it also makes me wonder, what if more than one thing goes wrong? Can parity bits handle that?
That's a great question. And you're right to think that basic parity bits have limitations. They're great at catching single-bit errors, like that single sock gone missing. But if you have multiple errors, the system might not detect them. It's like the sock drawer gremlin got extra mischievous and made off with both socks this time. That's where error correction codes, or ECCs, come in. They're like the super sleuths of data protection.
ECCs. Okay, so we're stepping up from a simple alarm to a full-on detective investigation.
Exactly. Imagine a detective trying to identify a single wrong item hidden among a lineup of almost identical ones. ECCs are like those detectives. They use clever math to not only spot errors, but actually fix them.
Hold on. Fix them automatically without me even knowing.
Precisely. One well-known ECC is called a Hamming code. Think of it as the Sherlock Holmes of error correction. It's remarkably adept at pinpointing and correcting those single-bit errors, all behind the scenes.
You know, it's amazing how all this happens without us even realizing it. It makes you appreciate how seamless data storage usually feels. There's this whole other world working tirelessly to keep our digital lives in order.
It's truly remarkable, but let's not forget about those bad blocks we talked about earlier, those damaged containers on our digital pantry shelves. Even with error detection and correction, what happens when an entire block becomes unusable?
Right. What does the system do when it encounters one of those? Does it just give up?
Not at all. The system has clever ways of working around those bad blocks. Our source mentions two main methods: sector forwarding and sector slipping.
Okay, I'm going to need some visuals here. Sector forwarding, sector slipping. It sounds like we're playing some high-stakes Tetris with our data.
I like that analogy. Imagine a big, organized library bookshelf. Now, let's say one of those shelves gets damaged. Sector forwarding is like taking the book from that damaged shelf and sticking it somewhere else in the library, maybe on a random shelf in a different section. It gets the job done, but it's not exactly organized.
So a bit of a shove it anywhere it fits approach. What about sector slipping? That sounds a bit more
orderly. Exactly. Sector slipping is like shifting all the books down the shelf to fill the gap left by the damaged one. The very last book on that shelf might get moved to a different shelf altogether, but all the books in between stay in their original order.
So there's a trade-off. Sector forwarding is quicker and easier in the moment, but sector slipping keeps things more organized in the long run.
You got it. It's all about finding the right balance for the situation. But these techniques mainly deal with individual errors. What happens when you need absolute certainty that your data is safe, even in a major crash? That's where the concept of stable storage comes in.
Stable storage, that sounds intense. What kind of situations need that level of protection? Stable storage, that sounds intense. What kind of situations need that level of protection?
Think about things like bank account databases, critical medical records, the systems that control power grids, data where even the slightest error or loss could be catastrophic.
Okay, yeah, that's a whole other level of don't mess this up.
Exactly, and that's where stable storage comes in. As our source explains, it all boils down to redundancy. Instead of relying on just one disk, stable storage systems use two disks that contain identical copies of the data. Let's call them disk A and disk B.
So it's like having a backup from the get-go. Double the data, double the safety.
Precisely. But it's more than a simple backup. These disks work together in tandem. If one disk fails, the other one instantly picks up the slack without missing a beat. And remember those ECCs we talked about? They're crucial here too. They're constantly checking for inconsistencies between the two disks. If a discrepancy pops up, they can quickly figure out which disk has the correct data and use that to repair any corrupted data on the other disk.
It's like having a built-in safety net for your most critical data.
A very robust safety net, indeed. Stable storage also introduces the concept of atomic writes to ensure that data is written completely and correctly every single time.
Atomic writes. Okay, now you're just using cool words. What makes it so special?
Yeah. It's about guaranteeing complete data writes. Think back to our half-baked cake analogy. With a normal write operation, a sudden crash could leave your data half-written and unusable. Atomic writes completely eliminate that risk.
So no more half-baked data. I'm liking the sound of that. But how do atomic writes actually work?
It's a two-step process. First, the system writes the data to disk A. Only if that write is 100% successful does it then write the exact same data to disk B. This two-step verification ensures that even if the system crashes during the write process, you'll always have at least one complete and uncorrupted copy of your data.
That's incredibly reassuring, especially when it comes to, say, my online banking information.
Exactly. But all this talk about redundancy and safety might have you wondering, doesn't all this extra checking and double writing slow things down?
You know, now that you mention it, that's a good point. Is it even possible to have both speed and this level of safety when it comes to data storage?
That is the million-dollar question. And it leads us to the fascinating world of data striping and RAID.
So we're talking about making things faster by using multiple disks. How does that work?
Imagine you're sharing a pizza with a friend. You could pass the pizza back and forth, each taking a bite, but that would be pretty slow, right? A faster way would be to split the pizza in half so you can both eat at the same time.
Makes sense. So we're talking about dividing and conquering the data.
Exactly. That's essentially what striping does. It spreads the data across multiple disks, allowing the system to access and process different parts simultaneously. This parallel processing dramatically speeds things up.
So more disks, Faster data. Sounds like a win-win to me.
It's a definite win in the speed department. But remember, adding more disks can also introduce more potential points of failure. If one disk goes down, it could affect the entire array. That's where RAID comes in, a redundant array of independent disks.
RAID. I've definitely heard that term thrown around, usually when people talk about high-performance computers. What's the deal with RAID?
RAID is a clever technology that combines the speed benefits of striping with the data redundancy we discussed earlier. It's like having your cake and eating it too, both speed and safety.
Okay, I'm hooked. Tell me more about how this data magic works.
Essentially, RAID combines multiple physical disks into a single logical unit. Think of it like this. You have a team of chefs in a kitchen, each responsible for a specific part of a dish. They work in parallel to prepare the meal much faster than a single chef ever could. That's the striping part, dividing the data cooking workload.
Okay, so we've got our team of data chefs all working together. Where does the redundancy come in? What happens if one of those chefs calls in sick?
That's where the redundancy part of RAID comes in. Some RAID levels have designated backup chefs, or disks, ready to step in if one fails. They contain a copy of the data from another disk, so even if one disk crashes, you won't lose any data. It's like having a recipe backup just in case a chef spills the sauce.
That's such a great analogy.
Yeah.
So with RAID, we're essentially combining the speed of parallel processing with the safety net of data backups.
You've got it. And just like there are different ways to organize a kitchen and different types of recipes, there are different levels of RAID, each with its own balance of speed, redundancy, and complexity. Some RAID levels prioritize speed, others prioritize redundancy, and some offer a balance of both. It all depends on the specific needs of the system.
So choosing the right RAID level is like picking the right tool for the job, depending on how much you're prioritizing speed versus data security.
Precisely. But the key takeaway here is that you don't have to choose between speed and safety. With RAID and other clever technologies, we can have both, ensuring our data is both accessible and protected.
Wow. I have to say, this whole deep dive has given me a completely new appreciation for what goes on behind the scenes every time I hit save. It's easy to take for granted, but there's a whole world of ingenious engineering constantly working to keep our digital lives from falling apart.
It really is quite remarkable when you think about it. We've only just scratched the surface of this fascinating field, but hopefully this gives you a glimpse into the intricate systems that make our data-driven world possible.
It certainly does. So next time you're waiting for a file to save or sending a photo to a friend, take a moment to think about the invisible army of bits, algorithms, and yes, even those hardworking parity bits, diligently working to keep your data safe and sound. It's a digital symphony happening right beneath our fingertips. That's all the time we have for today's deep dive. We hope you enjoyed this journey into often overlooked but always essential world of data integrity.